Hello everyone. In this video, I want to do something that will review your classic control all with a single example. So here we're going to consider a single system example, and then we're going to go ahead and create the transfer function of it, the state space of it, the space model, find the rise time, overshoot, settling time, steady state error, then go to the unity feedback system, find the type of the system, find its position, velocity, or acceleration error constant, the steady state error for the system for different types of inputs. Then assume that the controller is just a single gain, then do Routh-Locus, do Routh-Hurwitz for it, okay, and then adjust the gain to get a specific kind of response characteristic, then design the lead lag compensator in the time domain with basically Routh-Locus, then go to frequency domain, plot the Bode plot, Nyquist plot, get the crossover frequencies, phase and gain margin, the bandwidth of the system, then design a lead lag in the frequency domain, and finally design and tune a PID controller to achieve some performance goals. So going through this single example should literally review your entire course classic control for you. So I'm doing it because my controls class, they have a final exam coming soon, and I decided to make this exam for them and also share it with all of you wherever you are around the world. So you can review that entire course with one example. So let's get started. So here we have a simple mass spring damper system with an external force here. And the position of the object is x of t. And this is the mass M. It is connected to the wall by spring K and damper B. And this is my plan. This is the thing that I want to control the output of it, which in this case is X, the position. And we want to do all sorts of analysis on it. And there are numbers given for M, B, and K here. And the first thing we want to do is to find the transfer function of the system, which is output X over input F. So X of S over F of S. And that is very easy. All you need to do is to basically take a Laplace transform from this equation. That's all you need to do. So I'm going to go ahead and apply a Laplace transform to the system. So it is going to be m times s squared x of s minus s times x at time 0 minus x dot at time 0. And then plus b times s times x of s minus x at 0. And then plus k times x of s equals f of s. Now, when we find a transfer function, we should assume all initial conditions are 0. So we are going to get 0 for all of this, and then I can plug in the numbers for them. So this is 1, and this is 4, and this is 5. Now, if you do so and factor out x of s from both sides, you can see that on the left side you have x of s times s squared plus 4s plus 5. And on the right hand side, you simply have f of s. So from here, you can divide both sides by f of s and get the transfer function, okay, which is output Laplace over input Laplace. And that is clearly 1 over s squared plus 4s plus 5. Okay, so that is my transfer function done. Now, step number 2, it says find the state space model of the system if your state space variable are the position and the velocity, and your output is the position. Well, that is not very hard to do. So my state vector x is going to be basically the position x and its derivative x dot. if I take a time derivative from this, the state vector time derivative is going to be basically x dot and x double dot. Well, x dot, we just write it as is, but for x double dot, we go back to the original ODE and try to solve for x double dot. So I plug in the numbers here, and from here I solve for x double dot. If you do that, it is going to be f of t minus 4x dot minus 5 times x, and that is exactly what I'm gonna put down for you here. So negative 5x, negative 4x dot, and plus f. Now this one, you can clearly write it into a matrix format, so you can write it as a 2 by 2 matrix A times the vector x, which is x and x dot, plus a 1 by 2 matrix B times the input F. And clearly, if you look here, because inside this X, what you have is X and X dot. So how can you write this X dot as something times X plus something times X dot plus something times F? Well, all it is 0 times X plus 1 times X dot plus 0 times F. So one way you can write it is like this: 0 times x plus 1 times x dot plus 0 times f. And that 0, 1, 0 are the things that are going to sit in the first row. Then the second row is this one. Again, look at the coefficients: negative 5, negative 4, and 1. So that is what you're going to do. And there we go. This is my A matrix. This is my B matrix. So I got A and B. Now my output is simply just X, and that I write to this side. So Y, the output is simply X, which you can also write it as 1 times X plus 0 times X dot plus 0 times F. So you can write it as clearly a 1 by 2 matrix times the X vector plus a 1 by 1 matrix times the F, the input. And these coefficients are clearly going to be 1, 0, and 0 from here. So there we go. That is your C matrix. This is your D matrix. So you see, I found A, B, C, and D. There we go. So from differential equation, I could get my transfer function. I could get my state space. And if you want to make sure that your state space is actually correct, there is a sanity check you can do. If you plug A, B, C, D in the formula that converts it to transfer function, you should get this one back. And what was that? You know that the transfer function can be found from state space matrices through this formula: C times Si minus A inverse times B plus D. So plug those in here and see if you get the same transfer function. Well, let's do that. In this case, D is 0, so I don't need it. So if I plug in C is just 1 and 0, Si minus A has S on the diagonal and everywhere else negative elements of A. So it is going to be 0, 1, negative 5, negative 4. So this is what you are going to get. And then this is times B. And in this case, B was 0 and 1. Correct? Look, that's B. So if I calculate this, I should get the same transfer function. Do I? Yes. Because what is the inverse of a 2 by 2 matrix? Well, the inverse is going to be the diagonals swapped. So you're going to get S plus 4 here and S here. And the off diagonals negated in place. So it is going to be like this. And then divided by the determinant of it, which is S times S plus 4 minus 5 times negative 1. So if you simplify, it is going to be 1 and 0 times S plus 4 and 1, negative 5 and S, divided by S squared plus 4S plus 5, and the whole thing times 1 and 0 and 1. And you know, when you do that, basically this first part, if you do it, you are going to get only the top row elements. So you are going to get S plus 4 and 1. And if you multiply that by 0 and 1, you only get the second element, which is 1. So you get this one. And guess what? This is your transfer function. So you see, I could get the same transfer function through this important formula. And clearly, that's another sanity check that my state space matrices are absolutely correct. So that was the modeling part. Now let's go to part 2. Here we are going to plot the step, impulse, and ramp responses of the open loop system with G only, and then find from the step response rise time, percent overshoot, settling time, and steady state error. Now, I show you these responses, and you can also do it analytically as well. Maybe one of them I do analytically for you. And then, of course, we can use MATLAB as well. And then I also analytically and over the graph show you these numbers. So let's get started. For instance, let's say I want to get the impulse response of this system analytically. How? So in this case, X is going to be G times F. G is 1 over S squared plus 4S plus 5. And for impulse function, F is simply 1. So X of S is going to be that. Therefore, you take a Laplace inverse from both sides, and you can get X of T to be Laplace inverse of this. As you know, here the roots of the denominator are complex numbers. So if you know, the poles of the system are where? They are basically at -2 and then plus minus 2 squared minus 5, so -1. So your roots are at -2 plus minus I. Okay, you have two complex poles. This guy has no zeros, right? So your transfer function has no zeros. It has two poles at these locations. And you can also write this, if you want, in a quadratic form. You can write it as S plus 2 squared plus 1. Okay? So that is your transfer function. And as you know, if this 2 was not there for a second, 1 over S squared plus 1 is the sine of t. But since there is a plus 2, there is a 2-second delay. So your answer is going to be e to the -2t sine of t. There we go. So this is your damped sine response. And if you want, you can easily plot that, of course. Right? So if this is t and this is the impulse response, x of t, clearly at 0 you are looking at 0, at infinity you are looking at 0, and then it is going to be like a sine function that goes up, and then the amplitude starts shrinking, and ultimately it's going to go to 0. Yes? So that is what you are going to see. Okay. Clearly, it's an underdamped response, and in underdamped response, you can define different parameters like rise time, settling time, and so on and so forth. Now, here, this is for impulse response. What you define these basically characteristics for is the step response. So in that case, if you want to do that, then this 1 has to be replaced by 1 over S. And then here you're going to have another term that is added, and your response is going to go around a fixed number, and around that number the system is going to oscillate. Okay, now if somebody says around what number the system would oscillate, for instance, somebody says what is X steady state in this system in response to step input, what value would the system settle at? Well, let's find it. It's not really that hard. So based on the final limit theorem, this is equal to the limit of S times X of S as S goes to 0. So it is the limit of S. Now for, as I said, the step response, you have to use F of S equal 1 over S, and then times G. and let s go to 0, and clearly you can see that it is going to be 1 over 5. So 0.2 is the number that your system will basically settle around. So if you want to plot the step response of the system, okay, then if this is like 0.2, your response will start from here, and then it goes up, and then it goes down, and goes like that. Then clearly you can define rise time, settling time, and so on and so forth. Okay? By the way, if somebody says, what's the steady state error for the step input, what is it? Well, you know your input has magnitude of 1, is a unit step response. So if you plot the input, it is here at level of 1. So your steady state error is the difference between input and output. So the steady state error in this system is 1 minus 0.2, which is 0.8. Okay, so you can also see that in this graph. Now, if I want to find this time where your input reaches the final level of it for the first time, this is called rise time, correct? How much is that? Then what is this extra basically signal that is passing over the steady state value, which we call overshoot? What is the percentage of that? We can find that one. And then we found the steady state error already. And then at what time your system will be around 2% of the final value and never leaving that band, that is called the settling time. So if you want to find those, there is formula for that, and we can also do it over the graph. Okay, so let's go ahead and look at those, and we can also do a ramp response. Now for the ramp, if you want to do it analytically here, you have to do 1 over s squared, okay? But if you want to do it with MATLAB, I'll show you have to use the command lsim. So first, let me do these parameters, tr, percent overshoot, settling time, and so on analytically, and then we're going to do it in MATLAB. So I already did the steady state error for you. That should be 0.8. Now let's get the rise time, percent overshoot, and settling time. So what are they? The rise time, if you know the formula for it, that is pi minus some angle beta divided by omega d. What is omega d? What is beta? So beta is tangent inverse of, and omega d is omega n times this. Okay, and beta is the angle of the complex poles here, which is tangent inverse of that same square root over zeta. Okay, so it is this one. So if you plug in this system the values of omega n and zeta, you can get your rise time. So the first thing we need to do is to find the zeta and omega n in this physical system. So what are they? So here we have to look at the transfer function. The standard form of a second order system, as you know, it is omega n squared over s squared plus 2 zeta omega n times s plus omega n squared. So you can see that the denominators are the same, the standard format. The coefficient of s squared is 1. And therefore, you can see that omega n squared is 5 and 2 zeta omega n is 4. So from here, you can see that omega n is square root 5 radians per second. And as I said, 2 zeta omega n is 4. Therefore, zeta is going to be 2 over square root 5, right? And clearly this number is less than 1, and it should be because the response is underdamped response. And of course, you know, zeta has no basically units. Now you might wonder, what about the numerator? The numerator of this is omega n squared. So in this case, if this is 5, that should also be 5. Why is it not 5? Would that make any difference? No, not in terms of zeta and omega n. Not in terms of zeta and omega n. Zeta and omega n are coming from setting the denominators equal. So what happens here? Well, that 1, you can write it as a 5. So instead of 1, you can write it as 5 and then times 1 over 5. And now this is the transfer function that you compare against that. And then you might say, well, then what is the effect of this 1 over 5, huh? So what is this one doing? Well, that one is the response of this system. If you remember, the response of this system to step input is going to go to 1. So in this system, if you pass a step input, the output will also, the steady state value of the output will also be 1, and the steady state error in the system will be 0, okay, in this system. Because the output will go to 1, the input is at 1, so the steady state error is 0. In this system, if you remember, the output would go to 1 over 5 or 0.2. That 1 over 5 is exactly this ratio that you just have behind the transfer function. So that 1 over 5 is exactly this one here. So that constant behind that transfer function is causing the output to not converge to 1, but converge to 1 over 5 times 1, which is 0.2, and therefore you have a steady state error. So there we go. We found zeta and omega n, and then we are going to plug them in all of these different places. If you do so, your rise time is going to be 0.5928 with 4 decimals. Okay, so this is your rise time if you plug in the numbers. Then you might need the percent overshoot. So if you remember the percent overshoot formula is only a function of the damping ratio, and that is like an exponential function. So if I want to write it for you, if you remember, it is equal to e to the negative pi times zeta divided by that square root, and you have to multiply it by 100%. Okay? And in this system, if you calculate it, I did it with MATLAB, you can do it with any software that you like. Your overshoot percentage is about 5.9%. Your overshoot is not too much. And the reason is your zeta is actually close to 1. Okay, it's a big damping in this system. So you don't have a big overshoot percentage. So that is the percent overshoot. We calculated the steady state error in this system as I just showed you. And the last thing we need to do is to calculate the settling time. Now for settling time, you have to decide what criterion would you use. Is it 2% or 5%? So here I use the 2%, and the formula for it is 4 over zeta omega n. And if you do that, that number is clearly, if you look, your zeta omega n is 2, so it is going to be 2 seconds. Okay? Now, if you use MATLAB, MATLAB will not give you this number. The number MATLAB will give you is basically the number with decimals, because the actual time it takes it to be within a 2% band around the steady state value is not exactly 4 over zeta omega, and this number is less than 4. Here, this is like a conservative calculation or estimation of that. So this is bigger than the actual settling time. If you look at MATLAB here, I use the command step info in MATLAB, and the settling time that it gives me is about 1.7475. Also, pay attention when you give a rise time command in MATLAB, you have to tell it what limits, because although we define rise time in most of the textbooks as the time it takes the system to go from 0% to 100%, that is called the rise time. In some other textbooks and places, including MATLAB, the default is when it goes from 5% of the steady state value to the 95% of the steady state value. That time is considered the rise time, and that is also the default in MATLAB. So if you want it to go from 0 to 100%, you have to provide this rise time limits. Also, for settling time, the default in MATLAB is 4%, 2% criterion. So if you want to use the 5% criterion, where this numerator here, instead of 4, that's 3, then you have to also, again, give that to MATLAB and say, hey, the settling time threshold is basically 5 as opposed to 2, okay? So while the help is coming up, let me show you the other commands that I used here. So here is my system. The numerator is 1, denominator is m, b, and k. First, I use the tf command to form the transfer function. And you can see that. That's right over here. That's my transfer function. Then I use the command ss with those A, B, C, D matrices. And I can also form that system. Now, if you want to derive the A, B, C, D matrices from the transfer function, you can also do that. So instead of saying this, what you can say is basically matrices A and B and C and D are equal to transfer function to state space of numerator and denominator. And then this one will give you the numerator and denominator, the matrices corresponding to that, right? So let me run this command for you. Okay, sorry, wrong button pressed. F9, let's see. No, okay. So let me just run it here. There we go. And you get the same matrices that we have, or maybe different. You might say, these are not those matrices. You are right, they are not. If you look at this A for me, the top row and the bottom row are swapped, and the first row and the second row are column are swapped. Why? Because in this system, the way that MATLAB did it, MATLAB used the opposite of this. So in MATLAB, the x vector is considered as velocity as the first component and position as the second component. If you do that, then this is going to be different, because now your x dot is going to be basically -4 and -5, and then 0 and 1, right? Or 1 and 0. Yes. Okay, so that is going to be your A matrix. And then this B is going to be 1 and 0 because it's in the derivative of x dot, which is x double dot, that the F appears. And then the output, which is the second component in x, that makes this C to be 0 and 1 as opposed to 1 and 0. And that is exactly what you can see MATLAB has done. So if you see A, B, C, D matrices in MATLAB are different than the one you found, it doesn't mean they are wrong. They just used a different set of state variables. And you know that for one transfer function, there are infinitely many different state space models, okay? But if you think that the system is wrong, these matrices are wrong, as I said, you can use that formula I showed you and show that the transfer function is the same. How? So you say sims of S, and then you say, give me basically C times inverse of S times identity matrix minus A, and then times B plus D. Okay, and maybe you can do a simplify of that and write it also pretty. So that should show you the same transfer function that you earlier found by the command tf. If it does give you that, you're good. Otherwise, you made a mistake. So let me show you this. There we go. Look, you got the exact same transfer function. So those matrices are actually correct. And in terms of finding the step response, impulse response, and so on, as long as you have the transfer function of the system, all you need to do is to pass it to the command step and impulse, and that should give you the response. For the ramp function or any other function of time, you have to define a time range, you have to define the input, and then to get the output, you have to use the command lsim, okay? Linear system simulator or simulation. You pass to it your transfer function, the input, and the time. It gives you the output values and the sample time points for them, and then you can plot them versus each other, and these are these first graphs that you can see. Okay, so this is your step response. As I said, it is converging to 0.2. This is your impulse response, and this is your ramp response. And if you want, you can plot the inputs on the top of them, so you can here plot the unit step function here. Impulse is just not easily showable, and here you can plot a ramp function. Okay, so these are the first plots that you can get, and these are the values for the rise time, for the settling time. As I said, with this is the accurate one, not conservative one. This is the overshoot, and then if you want peak time and so on, you also have a peak time 1.20. Okay, so this is everything that we have done so far in parts 1 and 2. Now it is time to go to part 3. So part 3 says close the loop with the unity feedback system. It says, okay, now the desired input goes in, desired output, which in this case is the input of the system. This goes out. This is X, this is F. And let me make this a little bit shorter. And this is your G, and then unity feedback, which means basically the feedback transfer function H equals 1. So assume that your sensor is measuring the position of the object without any filtering or any type of distortion. So the signal that is being subtracted from the input, that is the exact same thing as X. In that case, the closed loop transfer function, remember, G over 1 plus GH, H is 1, and G was 1 over S squared plus 4S plus 5. So if you plug that G into here, your closed loop transfer function is clearly going to be 1 over S squared plus 4S plus 5 plus 1, which is 6. So this is your characteristic polynomial. And in MATLAB, if you want to get that, also you can do it with the command feedback. So you say, hey, give me the feedback of G and 1, which is H, and this is your closed loop transfer function. Now, what is the type of the system? You know, the order of the system is 2, clearly, because the highest derivative is 2, so order is 2. What about the type? Well, for the type, you need to, first of all, look at the G itself, not the closed loop. So you only look at G. And in this G, which in this case is this function here, if there are any poles at the origin, so it's like S to the N multiplied by S to the N, if you have N poles at the origin in the feed-forward transfer function, that N is type. Now, in this case, clearly S of 0 is not a root. So in this system, clearly the type of the system is type 0. And as you know, in a type 0 system, the system can follow the step input with a steady state error, but in response to a ramp and acceleration or parabolic input, the steady state error is infinity. Because if you remember, in general, the formula for a steady state error is the limit of S times E of S as S goes to 0, and E of S is the input of the system. In this case, in general, you can write it as R and Y, but in this case, let's say F and X. So that is this function multiplied by s as s goes to 0, and x, as you know, this is g of s times f of s. So if you factor out 1f, this is going to be the limit of s times f of s times 1 minus g of s as s goes to 0. And this formula is valid for any g, any f. Now, if the system has a step input, this is 1 over s, and this guy is what I just showed you, and this is 6. Now, you might say, didn't you just say g is that? Yes, but here, when we said x is g times f, this g here is the transfer function. So if I want to go with the notation I'm using here, I should actually say this is the closed loop transfer function times the input. So this is like t of s times f of s, if I want to go with that same notation. And here is also t. It's the closed loop transfer function that you use in the steady state formula. Now you might say, why didn't you use that up here when you calculated this error? Why didn't you use that? Because back then my system was open loop. Now my system is closed loop, so I have to use the closed loop transfer function. Okay, now I brought in a feedback and I closed the loop in this system. So I have to use the closed loop transfer function. Okay? And in this case, if I calculated this s and 1 over s would cancel, you get 1 minus 1 over 6, you get 5 over 6. This is your steady state error in response to step input for the closed loop system, not the open loop system. If you plot the step of the closed loop system, then you'll see that the output of the system goes to 1 over 6 as opposed to 1 over 5, and there is 5 over 6 error. Okay, and then what is Kp? Well, Kp, if you remember, is g at 0, and this steady state error is equal to 1 over 1 plus Kp. So clearly Kp in this system is 1 over 6. And your steady state error, as I said, is 5 over 6 in response to the step input. Okay, what about Kv and Ka? Well, for those here, we can look at other types of inputs. For instance, we can look at the ramp. So if ramp is there, then this is going to be 1 over s squared. And this one is going to be 5 over 6, but here you have 1 over 0, so it's going to be infinity. So in response to a ramp input, the steady state error is going to be infinity, which is equal to 1 over kV. And kV is the limit of s times g of s, in this case t of s actually, as s goes to 0, which is 0. And clearly 1 over 0 is infinity. In other words, the system cannot follow a ramp input with even a constant error. The error is going to get bigger and bigger. And the same thing goes for the acceleration. For acceleration also, or parabolic input, where this here is going to be 1 over s cubed or 2 over s cubed. The result is the same. Steady state error is going to be infinity again. It's going to be 1 over k times a, where k times a is the limit of s squared times t of s, and that is also 0. Okay, so the system will show infinite error to ramp input and parabolic input. Here I have generated both of them for you, so you can see the step, impulse, and ramp responses of both open loop and closed loop system. Now both of those systems are type 0, so the responses are very similar to each other. You see that the gap between the ramp and the input of the output of the system in both cases is increasing, so it goes to infinity when t gets very big. For impulse, there is no worries, and for the step, both have a constant steady state error. Now, although they look very similar, but their final values are not exactly the same. if you look at the closed loop system, the output of that, you see, it's basically 1/6, while if you look at the open loop system, it is at 0.2. Okay, so you clearly see that whether you use the G or here 1/1 plus G, the results are, of course, a little bit different. And one other thing I wanted to show you, remember I said Kp is G at S of 0. There is a name to this value here. Okay, this one here is also called the DC gain of the system. So in this system, closed loop DC gain is 1/6. In the open loop is 1/5. And in MATLAB, there is a command for it, DC gain. So when you look at my code, when I release it and you can look at it, if you see the command DC gain somewhere, that is basically the G at 0. And this is what I have done. So now that we have seen all of that, it is time to go and look at the Routh-Locus. So you can sketch the Routh-Locus now with a simple gain. So now all you do is in this system, now you add a gain to either G, or you can add it as a controller. So now your controller in this system is simply a gain. Let me plot that for you. So this is your controller, a simple gain, and you want to know what happens in this system for different gain values, what kind of closed loop transfer function poles you will get. So we want to look at the poles of the transfer function versus this gain, because now if you look at your closed loop transfer function, if I call it T again, it is K times G, because that gain K and G are in series, over 1 plus K times G times 1, which is H. So in that case, remember G was 1/s² plus 4s plus 5. So you get a K here, and this is going to be divided by 1 plus that. So you are going to get basically s² plus 4s plus 5 plus k. So now the roots of this, which are the poles of the system, they do depend on k. And that is the Routh-Locus. We want to plot the location of these two poles of the system versus gain k. That is called the Routh-Locus. Now, in this case, you know, when you do Routh-Locus, you only do it based on the open loop transfer function, which is the product of all of these. So the function that we should focus on for the Routh-Locus is simply k times g. So this is the function that we should be focusing on. This is your open loop transfer function. We focus on that and we draw a Routh-Locus for it. Now, clearly, the system has no zeros, so the number of zeros is 0. The number of poles is 2. It has 2 poles, okay? And so you only will have 2 branches, starting at the poles and going to zeros at infinity. And then, for instance, the angles of the asymptotes, they are plus and minus 2k plus 1 times 180 degrees divided by n minus m, where k goes from any number from 0 to n minus m, which in this case is 2. So k could be 0, 1, and 2. If I plug in 0 here and n minus m is 2, your angle will be plus and minus 90 degrees. If I plug in 1 here, you're going to get plus minus 270. And if I plug in another one, it is going to be plus minus 450. And all of these angles are the same. Basically, they are the same, plus minus 90 degrees. The intersection of the asymptotes where the asymptotes will hit the real axis, that is equal to sum of the poles minus sum of the zeros divided by n minus m. Okay? So if you look at this system, remember it has no zeros, and if you remember, the poles of the system were at -2 plus I and -2 minus I. So sum of the poles is going to be -4. There is no zero. N minus m is 2. So -4 divided by 2, it's at -2. So your asymptotes should intersect the real axis at -2. And let me start drawing the Routh-Locus. So we do it in the complex plane. This is your real axis. This is your imaginary axis. The poles are here. One is there, one is there. There is no zero. If there was, you have to add a hollow circle for it. The intersection of the asymptotes is also here. And the angles are plus minus 90 degrees. And the parts of the Routh-Locus on the real axis is any place that sum of the poles and zeros of the open loop to the right side of it is an odd number. So if I put my test point here, right? So let me put it here, for instance. How many points to the right side of it I have from the poles and zeros of the open loop? Nothing. And nothing or zero is an even number. So this part cannot qualify. If I come here and put it, again, to the right side of it, there is 0 pole and 0 of the open loop. So that doesn't work. If I put it here, then there are 2 to the right side of it. And 2 is also an even number. That is not an odd number. Therefore, this Routh-Locus basically has no extension, nothing on the real axis, okay? The Routh-Locus will never be on the real axis for this system, okay? There is no part of it on the real axis. We calculated the asymptotes and their basically angles. Now we can look at the other things in the Routh-Locus. One of them is the intersection of the Routh-Locus with the imaginary axis that we can do. Then we have the breakaway and break-in points, the angle of departure and arrivals, if there is any, and so on and so forth, right? So let's go ahead and do that. By the way, in MATLAB, there is the command rlocus that can give you the Routh-Locus, in this case for G. And if you want, you can see the Routh-Locus. So let me show you the Routh-Locus in the system. Before we can also, as I said, I'm working to plot it here. But this is the Routh-Locus of it. You see, one directly goes up, one directly goes down. That's all it is. Okay, that's all you can do in this system. Your Routh-Locus directly goes up and down. Okay, nothing else. So, but let me show you why it is like that. Okay, because yeah, in MATLAB you just type in a single command. It doesn't mean that you really understand why it is behaving the way it is behaving. So first thing is the intersection with the real axis, with the imaginary axis. So in that case, what you need to do is in your basically characteristic polynomial, you can plug in s equal j omega, because if it hits the imaginary axis, the value is going to be some omega, which we don't know, times some j of the complex number, or I if you want. Here I used I, so I'm going to call it I times omega. Okay? So the question is, how much is that omega and how much is the gain for that point? So again, all you need to do is in the characteristic equation, which is this guy here, go ahead and plug in s equal I omega. So we get I omega squared plus 4 times I omega plus 5 plus k equals 0. Now I omega squared is negative omega squared. So if you rearrange it, it is gonna be 5 plus k minus omega squared plus I times 4 omega. This is equal 0. Now a complex number is 0 when both parts are 0. Therefore, we can say both of these are equal to 0. And here you clearly can see that omega should be 0. And from here, if you plug in omega of 0, k is going to be negative 5. And you know that in a Routh-Lucas, this gain k is always positive. And the fact that it says for k of negative 5 you hit here, that means there is no intersection here with the imaginary axis. So Routh-Lucas in this system will never hit the imaginary axis. Okay? Now, does the system have any breakaway or break-in points, the points where the Routh-Lucas gets off of the real axis or enters the real axis? Now, clearly, the answer is no in this system. Why? Because there is nowhere on the real axis that the Routh-Lucas falls on, and therefore, it can never come and hit the real axis. Therefore, there should be no breakaway or break-in points. But if you also want to show it, then you have to write your characteristic equation, which is this one. You have to write it in terms of k, so you have to find k as a function of s, and then take s derivative from that and set it equal to 0. The roots of that are breakaway and break-in points. So let me go ahead and do that. So from that characteristic equation, if you set it equal to 0, k is, and take everything to the other side, is going to be negative s squared, negative 5s, negative 5. 4s, negative 5. Now take a s derivative from both sides of this. You get negative 2s, negative 4 equals 0. And you see s has to be negative 2. But is s of negative 2, is this point allowed on the real axis? We remember that it doesn't. No point and the Routh-Lucas in this system falls on the real axis, so this one is not acceptable, and of course there is no breakaway or break-in points. Okay, and then finally, angle of departure from the poles. Angle of departure from the poles, the formula for it is, if I move a little bit to this side, the angle of departure, let me move, there we go. So the angle of departure from a pole is equal to 180 minus sum of the angles from the other poles plus sum of the angles from the other zeros of the open loop. Now this system has no zeros, that's it. So for instance, for this guy, all I need is to connect the other pole to it with this vector, and then I measure the angle of this vector with respect to the x-axis. So if I call it phi, this is just minus phi, and there is no zero. And in this case, phi is simply 90 degrees, so 180 minus 90 is 90 degrees. So in this system, the Routh-Lucas should get off of that pole with the angle of positive 90 degrees. And what does that mean? It means it goes straight up like this. That should be the Routh-Lucas, right? The Routh-Lucas goes straight up from that point and goes to infinity. And since Routh-Lucas is always symmetric with respect to the real axis, the other part of it is going to go down like this. So these are your two branches of Routh-Lucas, and that's all it is. This is your Routh-Lucas. There is nothing else in this system. It's very, very simple. That is all your Routh-Lucas, and as I showed you in MATLAB, the command R-Lucas is going to get that done for you, right? So here is that command here again, and these are the two branches of Routh-Lucas. This is your imaginary axis. You see there is no intersection, there is no part on the real axis, and that is my Routh-Lucas of the system. Okay, so we did the Routh-Lucas. Now it says choose a desired settling time of 1.5, adjust the gain k to meet this requirement. So set gain k so you get a settling time of 1.5. If you remember your open loop system, your settling time, let me find it for you. Your settling time was 2 seconds. Now, can I change this gain to bring it down to 1.5 seconds? Is that a possibility? Well, remember the settling time is equal to 4 over sigma, and sigma is zeta omega n. And for these guys, that is that sigma. So in this system, whatever you do at poles, k equals 0, and as you go to imaginary zeros, k goes to infinity. So regardless of what you do, the poles always in this system will have a sigma of 2. And so your settling time in this system is going to stay at 2 all the time, regardless of what you can do with k. It's not a possibility. There is no way in this system that you can set the settling time to any number other than 2. Okay, so the answer is, can I pick any gain? No, I cannot. But you might pick gain k to achieve something else. For instance, in this system, if you remember, the overshoot percentage, let me find it, it was basically 5.9%, or the rise time was about 0.6 seconds. Can I change those by changing gain? The answer is yes, you can. Right? So remember, the overshoot of the system, the percent overshoot, that is a function of damping ratio only. Correct? And so if you pick a specific overshoot, that means you are picking a specific damping ratio. And picking a specific damping ratio in the Routh-Locus means picking a specific radial line, where if you draw that radial line like this, for instance, this angle here, whatever that angle is, cosine of that angle, which we called beta in our notations, that is equal to the damping ratio. Okay? So I can pick any specific overshoot, specific xi, and as long as that radial line with that specific angle intersects my Routh-Locus, that means I can achieve it. Now, clearly in the system, your angle cannot be less than this angle here, right? This angle is the minimum angle or the maximum zeta that you can have, and that is the zeta that we had in the system, 2 over square root 5. So in this system, I cannot improve the overshoot anymore. There is no way I can reduce the overshoot from that 5.9%. I can make it bigger. And you might say, why would you even make it bigger? What's the point? Having a bigger overshoot, what does it give us? Well, you can achieve instead with it a faster rise time, because rise time and overshoot are typically the opposite of each other. You can make the overshoot go up at the instead you can make the rise time go down. Okay, so can I achieve that? For instance, they might say, well, make your overshoot go to some bigger number, but when it happens, what would you gain? Because if I get a bigger overshoot, let me clean up here a little bit. If instead of this point, I go to here, I have now a smaller xi. Okay, so this one has a smaller zeta. But what does it have bigger? Well, remember this radial line here, that is omega n. So this one here has a bigger omega n. And omega n appears in the denominator of the rise time. So I might be able to achieve a bigger or smaller rise time in price of some overshoots, right? So let's say, for instance, in this system, if I change my overshoot from 6% to maybe 10%, what would happen to my rise time, what gain do I need, and so on. So the first thing is I go back to my formula and I say I allow 10% overshoot. So from here, go ahead and determine my zeta. And then I can also determine my omega n and then rise time and everything. So first thing, I take a natural log from both sides, right? I take a natural log and then square both sides and cross multiply. If you do so, you get pi squared zeta squared equals 1 minus zeta squared times natural log of 0.1, the whole thing squared. And from here, I bet you can find the corresponding zeta. Let me calculate that for you. So your damping ratio goes to something like 0.35. So you need a smaller damping ratio to achieve that, while initially your number was 2 over square root 5, and that 2 over square root 5 was 0.89. So my initial damping ratio, let me see here, this one was 0.89. Now I'm allowing it to go down to 0.35, so I can go from 6% overshoot to 10% overshoot, okay? If that's the case, how much is my omega n? Well, omega n in this system, zeta omega n in this system for any pole has to be equal to 2. So when zeta goes to 0.35, omega n is going to go to 2 over 0.35, and that number is going to be, let me calculate it in MATLAB, it is going to be 5.71 radians per second. You see, my omega n increased, my zeta went down. Remember my original omega n? Look at it. It was just square root of 5 in the beginning. Now it is over 5 units, so it was 2.34. But now it is 5.71. Now with these ones, what is your new rise time? So let's go ahead and calculate the new rise time. And guess what? It is going to be 0.36 seconds. Well, initially your rise time was 0.59. Now I could bring it down to 0.36. So you see, I sacrificed some overshoot and I could get the system to have a smaller rise time. And I did that by moving my poles from basically a point here to somewhere here. Now the question is, where is that somewhere and what is the gain for that somewhere? Okay? Right? So in this system, you might say, choose a rise time instead of a settling time, which is not possible. Bring down your rise time from 0.59 seconds to 0.36 seconds. What gain do you need to make it happen? And I'm going to show you that one right now on the Routh-Locus. We can do that. And I also show you how to do it analytically. So let's go ahead and use the data cursor in the Routh-Locus, and I'm going to, wherever you click, it is going to give you the information for it. So look at the damping. Damping of this point is 0.60. Remember, your damping in this system, damping ratio is basically, as we calculated, 0.35. So you have to move it such that you get to the point of 0.35 damping ratio, right? That is not possible. So I move down, see if I can get to 0.35, if that's a possibility. Oh, I move up actually. 35, seems like I need to, and it is not even showing me all the way up there. That's interesting. The maximum this one did is somewhere close to a gain of, if you can see, a gain of 23, but it's smaller than that, right? Or bigger than that. Because look at my damping ratio, it is 0.39, 0.37. It jumped from 21 to 23, so if it doesn't show it, but if you want, you guess probably it's around 25. It's around 25 that you get that intersection point. So how do I calculate it analytically? Now that I know where my poles are, correct? Now that I know where my poles are, how can I calculate this? So first, let me calculate the location of the pole exactly. Now that I have zeta and omega n, if you remember, your poles locations are at the real part of them is zeta omega n, and the imaginary part of them is omega n square root 1 minus zeta squared. Now that I have this zeta and omega n, this guy is going to be 2, and that one, if I calculate it for you, let me do it in MATLAB for you a second. And so you get 5 times 7.1 times square root of that number, you get 5.35. So your location is -2 and 535. This is where your pole is. And the question is now, what is the gain at that point? So how do you find the gain at any point? And the formula for it is the gain at any point is equal to product of length between this point and the other poles, okay, divided by the product of the distance between the zeros to this pole. So I can call it something else, for instance, Ri. So di's are the distance between the other poles to this one and the zeros. Now, in this case, you only have these two poles of the original system. There is no zero. So if you find this distance, which is, you call it D1, and if you find this distance, which you can call it D2, there is no R, so this whole thing is a 1. So simply, in this case, it is going to be D1 times D2. So if you find the distance from this point to the original two poles, which were at -2 plus minus I, that should be your gain. How much is it? Well, their x's are all the same. The y's are different. So this one is at 535. One distance is to the 1. One distance is to the -1. So one of these guys is 531 minus 1, which is 435. And the other one is 535 plus 1, which is 635. So if you multiply these two numbers together, that should be the gain at that location. And let me do that one for you. And the number is 2762. So that is exactly the gain where you need the poles of the system to have a rise time of 0.36 seconds. Okay, so remember, your original Routh-Lucas command does not even go up to that gain. Now it says, what range of K makes the system stable or unstable? In what range of K the system is stable? Well, clearly, looking at the Routh-Lucas, the system is always stable regardless. Why? Because the Routh-Lucas will never ever go to the right side of the imaginary axis. You never have poles on the right hand side. So regardless of what K you pick, the system is always stable. So the range is 0 to infinity. Can you show that with the Routh-Hurwitz? The answer is yes. I can show you also that the system never gets unstable by changing K using the Routh-Hurwitz criterion. How? I go ahead and I apply that to this characteristic polynomial, s squared plus 4s plus 5k. So let's go ahead and form that table for this case. So that's my characteristic polynomial. I have 3 rows, s squared, s to the 1, s to the 0. And for this one, the coefficient is 1 and then 5 plus k. For this one, it is 4. This one you don't have, so you artificially add the 0. And here, this one is going to be 4 times 5 plus k minus 1 times 0 divided by 4, correct? So let me write it for you, which is simply 5 plus k. And now you look at the coefficients in the first row. So you look at this one, you look at this one, and you look at this one. And remember that this k here, this k is always positive. Now look at the first row. The number of poles on the right-hand side is the number of sign changes in the first row. Well, in the first row, everything is positive. There is no sign change, so there is no pole on the right-hand side whatsoever for any value of k. Okay, and therefore, the system can never become unstable for a positive gain. And that is what we always use in Routh-Lucas. Okay, so you see that whether you use Routh-Lucas, or use Routh-Hurwitz, the answer is you cannot make this system unstable. So the range is infinity. Okay, now that we have that, it is time to go to the time domain, and it is time to design a lead lag compensator. So we are going to look at that one, but clearly you see that I have 4 other tasks that I need to do: lead lag compensator in time domain, frequency domain analysis, lead lag compensator in frequency domain, and PID. And if I want to go through those 4 tasks, this video, instead of 1 hour, 12 minutes, is going to be like 2 hour, 2.5 hour, and it's going to be a very, very long video. So if you okay with that, I'm going to cut this video right now, and I'm going to make it part 1, and then I'm going to make a second video, call it part 2, and in that part 2, I'm going to continue on these 4 tasks. So let's finish this video right here, and soon I'm going to start the second video. Thank you.